So we're now recording. So folks in chat again asked to talk through the multiple choice questions here. Um, so oops, I need to do that. I did something that messed up my screen. Eep. There we go. Now it's fixed. So the first segment asks you to think about whether the things that are presented here are dimensionally correct or not, whether their dimensions match. 1 second, let me type in the URL in chat. So it's posted on the course website, but a direct link, Joseph, is that one. Okay, so the first segment says, tell me which things contain a dimensional mismatch or not. So we'll talk through all of them. So the way to figure this out is to look at each item in all of these equations and try to figure out what it is, like what kind of thing it describes. And if you can't recognize that right away, you can always look at each individual symbol and say, okay, what are the units of this thing? So I will ask you about these. We'll talk through them together. So this is something where I need your input. When you see, let's do this one first. So v naught sine theta, what kind of thing is that? Is that a distance? Is it a time? Is it an acceleration? Is it an angular velocity? Is it something that's unitless? What is that? Yeah, it's a component of a velocity vector. Yeah, it's not a vector itself because v naught is, the magnitude of something, but this is a velocity. What is this? 1/2 mu gt squared. So again, is this a distance? Is it a time? Is it an acceleration? Is it a force? Yes, it's a distance because you know that 1/2 gt squared, that is a piece of the position formula in kinematics, and mu is dimensionless. So you could, if you realize that, say, this is a distance. But if you don't, you could say, all right, g is an acceleration, so it's got units of meters per second squared. Mu is a pure number, it's dimensionless. And t squared has units second squared. So meters per second squared times second squared is just meters. So regardless of how you get there, this thing is a distance. So I can't add a distance to a velocity, so this one contains a mismatch. So that's how you do all of these. So let's talk through all of them then. What kind of thing is 1/2 m1 v1 squared? Yeah, you recognize that as the formula for kinetic energy. Can you only multiply a distance and a velocity? So the idea, Martina, is that you cannot, yes, you could multiply them. You could say 10 meters times 5 meters per second is, 50 meters squared per second. But you cannot subtract them. You cannot subtract two things of unequal units. Like imagine, what is 10 inches minus 2 liters? You can't subtract an amount of liquid from a distance. Yes, exactly. If it was velocity plus velocity, you could do it. Um, yeah, you got it. So you all have told me that this term is an energy. Energy has units kilograms meters squared per second squared. So Joseph, you can convert things between different units that measure the same quantity. So you could convert, say, liters into gallons, into cubic inches, into, um, I don't know what else people measure volume in, fluid ounces, but you can't convert a number of gallons into a number of inches because they measure different kinds of things. Like you could convert inches into miles or feet or meters or centimeters, but you couldn't convert a number of inches into a number of kilograms. So unit conversions will not let you um, match things that are of different dimension. Um, so 1 half mv squared is an energy. What's the next one? What is mu mgd? What does that, and if we don't recognize that from an equation somewhere, then we can always just look at what all of the units are. But does anybody want to like give an intuitive stab? Yeah, that looks like a work done by friction, as Lisa and Samuel have said, and that is also an energy. Okay, what about this thing on the right? Yeah, so Avery has done at all the units. That's kilograms times meters per second times meters, which is kilograms meters squared per second squared, um, which is an energy. What about that term on the right? Is it also an energy? No, I, I don't actually know what it is, right? This is not an energy. This is just something that I made up that was wrong. So this to be an energy would need to be something like 1/5 m3 r squared omega, because that looks like a moment of inertia times, well, omega squared. So this is a moment of inertia times an angular velocity squared, which is an energy. So this one also has a mismatch. Okay, what about C? Tell me about this one. Obviously, this is a force, right? What is M1G? That's a weight. Is weight a force? Yep. Yep. So this is a force. And in the denominator, we can pretty clearly see that this is a mass. So is acceleration equals force over mass dimensionally correct? Yeah, that's Newton's second law, right? So that one's fine. Um, what about this one in part D? How are we going to do that? This one's tougher. Well, so what we need to do is figure out what that is under the square root. So m over k what units is the spring constant in? Okay, this is a really good point. So how do you figure out what units k has? So what does the spring constant tell you? M is obviously kilograms, but K tells you how many newtons of force. Yes, it's newtons per meter. Exactly. How many newtons of force per meter of stretch? So it's got units newtons per meter, as Samuel has said. So this is newtons per meter. So we have, I'll draw a line here. M over K is kilograms divided by newtons per meter. Now, do we have a way to simplify this? Well, we need to know what a newton is. Now, how do we figure out what kind of dimensions a newton has? Well, we know force equals mass times acceleration. Yes, exactly, Avery. We know that since F equals ma, a newton must have the units of a mass times an acceleration. So that means this is kilograms divided by, well, we'll write it this way, kilograms meters per second squared per meter. And so this is m over k. So now we can start canceling things. We can cancel the kilograms, we can cancel the meters, and we have 1 over seconds squared, which is just seconds squared. So that means that the square root of m over k has units of seconds. So any questions about how we did that? We just took apart the units of k. We saw, okay, k is a newton per meter, which is a kilogram meter per second per meter, and then canceled everything and then took the square root of those units. So does this equation here, D, make sense? Yeah, it does, because it has units of seconds, and that was supposed to be a time. So this one is yes. All right, what about E? I'll let somebody in chat volunteer this one. Tell me if this equation makes sense and why or why not. How you knew. Obviously, these terms are velocities, but tell me about what's under the square root. Is that the sum of forces when using an incline? Yeah, so Avery says it doesn't work. Joseph says, is that the sum of forces on an incline? Yeah, so you kind of recognize this as like g cosine theta kind of looks like a normal force times a coefficient of friction. Mg sine theta, well, that looks like a component of gravity. So yeah, this is pretty clearly under here the square root of forces. And I don't know what the square root of a newton is, but it sure as hell is not a velocity. So yeah, that one doesn't match. Um, so all of you are like telling me what these things are. You're recognizing these algebraic expressions, and let me kind of let the cat out of the bag and say why this was on last year's exam. Like these questions were taken straight off of last year's exam. And not all of these were, but these were. Because one of the crucial things in doing physics or engineering is being able to look at an algebraic expression and understand the story it's trying to tell. So for part D, we had to work hard here because we haven't seen this square root mass over spring constant thing before. It turns out it does occur. and you'll see that in more advanced study of mechanics. When you study vibrations. Um, so here we had to take all the units apart, but in all of these others, these terms are like things that you recognize, things that you have seen before. And so these questions, the easy way to do them is to recognize what these algebraic expressions refer to, and you're kind of building up your vocabulary. It's like teaching people to read. So when my mother did this, my mother was an English teacher, and when you're teaching people to read in the beginning, they have to like sound out words and kind of think about what sounds the letters make, and then put all those sounds together and say, "Oh, I know this word." And then as you gain more proficiency in a language, right, you see a word and you say, "Oh, I know what that is. I've seen that before." So these questions are both testing whether you understand how units work, but also kind of generally testing your fluency in the language of physics. Um, let's talk about number F. So does F make sense? Yes, yes, it does. So I'm going to pick on somebody. I'm going to pick on Joseph. You're correct, but tell me why you said yes. How did you figure that out? Actually, I'll have everybody who said yes, all four of you, type out to me why you said yes. You recognized it from past homework. Okay, so that's another fluency in language thing. You kind of multiplied R over in your head and the units matched up. Yeah. So Aiden says, yeah, because an acceleration times time is a velocity and v over r is omega. Yeah, so you're all saying, okay, I've seen these things before, right? So this is a velocity. This is a distance. And you know that omega is v over r. So yep, that one checks out. What about this one for g, the last one? Yes, it does. How'd you figure that one out, Kalhako? Aiden? Actually, so this on the left-hand side, this is actually little g, because little g is the force of gravity divided by the mass of the object that's falling. So that's gmm over r squared divided by little m. So you recognize the thing on the left as an acceleration, and you can recognize this thing on the right also as an acceleration, because that's the formula for centripetal acceleration. So this one also checks out. So any questions about that segment of the multiple choice? We'll do all of these here. I'm happy to work through the entire practice exam if that's what y'all would like me to do. Um, anything about these before we move on? Are you going to have a question like this on the test? You might. Regardless, the skill of being able to look at something and know dimensionally what it is, that is a very valuable skill because it lets you check your work to see if you've made an algebraic mistake. I kind of mentally do this in my head as I'm working a physics problem, and if I ever get something that doesn't check out, I stop and I say, I know I've made a mistake. So you may or may not have a question like this on the exam, but regardless, it's a skill that will help you on the exam. Okay, if there's nothing else about that, let's move on to number 2. So we'll just go quickly through these. The work done by gravity on an airplane flying horizontally at a constant speed. So here, this one, well, work is force times the distance displaced in the direction of that force. So here the force goes straight downward, but I'm moving straight sideways. I'm not moving up or down. So here this is 0. Um, Tell me about the next one. The work done by gravity on an airplane flying diagonally downward. Could I move the page up 1 second so you can screenshot it? Certainly. Negative. Actually, no, hang on, Isabel. Is gravity in this case making the airplane, is it trying to speed it up or trying to slow it down? So remember, work is force times the displacement parallel to that force. Yeah, it's making it speed up. So yeah, no worries, Isabel. So this one is positive. Okay, tell me about the rotational kinetic energy of a wheel. Is that positive, negative, 0, or could it be multiple of those? Well, I don't know, Grace. Maybe it's moving, maybe it's not. Too many what ifs, yeah. So, so okay. Some people say positive or 0. Kalhaku's saying it depends on direction. And yes, Grace, that's exactly it. The velocity is squared. So in classical mechanics, you cannot have negative kinetic energy because um, translational kinetic energy is 1/2 mv squared. Rotational kinetic energy is 1/2 I omega squared. So those things could only be positive or 0. But it could be 0 if it's not moving. It turns out in quantum mechanics, you can have negative kinetic energy. But we're not doing quantum mechanics here. Okay, tell me about the gravitational potential energy of a rock near Earth. Okay, Aiden says it's positive. Kalhaku says it could be 0. Could it be negative? No, it's a rock just like around here somewhere. Maybe it's one of the ones. Maybe I have a rock in my apartment and I throw it out my window. Um, so you're saying 0. Could it be positive? Maybe I hold the rock above my head. Yeah, and that's the hard one, Grace. Could the gravitational potential energy of a rock be negative? When is gravitational potential energy negative? So remember that if I have some system, right, if I have, something happening, I don't know what it is, maybe it's, some kind of ramp and I have some ball up here, I could define any point I like to be my 0 point. So as an example, if I've got a pendulum swinging back and forth, right, I could say that this point up here was y equals 0, or I could say this point is y equals 0. Um, yeah, so you have freedom to choose anywhere as 0. Um, remember, another way to see it is potential energy is mgy, and you have freedom to pick your coordinate system. So you have freedom to choose where y equals 0, and if you're below that, then gravitational potential energy would be negative. So Joseph, if you throw something upwards, then again, whether you have positive or negative potential energy depends on where you choose your 0 height. If you choose y equals 0 to be at your hand, then it would have positive potential energy if it's up in the air. But if you choose your 0 height to be somewhere above you, then it would have negative potential energy if it is below that. Yep, exactly. This one is all 3 because we have freedom to choose our coordinate system. What about the elastic potential energy in a spring? Yes, these are tricky, Martina. These were quite difficult last year. We usually don't do tricky, but I guess these could be. Okay, so the elastic potential energy in a spring could be positive. Could it be anything else? Um, would it depend on what state it is? Okay, so this one is, people have said positive. It depends if it is stretched or pressed. Okay. Lisa, could you tell me what you mean by that? Yeah, when it's not deformed, it's 0. So that's completely right. But could it ever be negative? No, it can't. The formula way to see that is that the elastic potential energy is 1 half k times the stretch or compression distance squared. So that cannot be negative. Um, another way to think of it is whether I stretch or I compress a spring, when I let go of it, it's going to do positive work on something. It's going to push something in the direction that it moves. Like the force will be in the same direction as the motion. So that one cannot be 0. Um, what about, yes, exactly, knowing the formulae can help you here. Um, tell me about the work done by static friction on a car driving down the road. Mm. We have positive and negative. Okay, so Aiden and Joseph, why don't you tell us why you said either positive or negative? Ah, okay, so Joseph is saying friction goes in opposite direction of motion. Um, is that always true? Yeah, Lisa said, but friction here can be traction. So if I have a car driving at a constant speed, right? So here are the wheels, here's the car, here's the road. The traction force actually points forwards. Yeah, because here, what you would need to know is if I'm going at 120 kilometers per hour, that's pretty fast, right? So if I don't have an engine constantly pushing me forward, then air resistance will slow me down. So the work done by static friction has got to be forward. That's why we have to put engines in cars, right? Um, so here the work done by static friction is positive because that traction force of static friction, remember traction is a special case of static friction, that traction force is what sustains my car's motion in the face of air resistance. This next one is tough. Um, there is a homework problem that we gave last year and chose not to give this year where you calculated this directly. So this was on last year's final exam, and it was um, at that point, like straight out of the homework. But we haven't done that on the homework this year. Um, so if a ball is rolling downhill, can you use conservation of energy? Let's start there. Even though we haven't done this, we can figure it out. So if I give you a hill and say there's a ball up there, um, and I ask you its velocity at the bottom, can you use conservation of energy? Yes, you can. And what that means, if you can use just conservation of energy without thinking of the work done by friction, that means friction does no work. Does it come to a stop at the bottom? No, we're asking about its velocity at the bottom. So presumably it keeps on going. Another way to see that is, yes, static friction is required to make something roll without slipping down a hill. But in that case, static friction does negative work on its translation, but positive work on its rotation because it makes it spin. And you can show with some math that we did last year but didn't do this year, that this is 0. So that question, we wouldn't put that on this year's exam. Okay. Tell me about the work done by Earth's gravity on a rocket flying from Mars to the moon. Why positive, Eden? You're right. Does it depend on where the moon is relative to the Earth? Um, it depends on where the moon is relative to Mars. So you know that Earth's gravity pulls things closer to Earth, right? And Mars is further away than the moon. Regardless of where the moon is, regardless of where Mars is further away than the moon. So as you go from Mars to the moon, you are getting closer to Earth. And during that motion, Earth's gravity will do positive work on you, regardless of kind of which side the moon is on. Yes, there may be some small piece of the trip where Earth's gravity does negative work on you, but the overall work is positive because you got closer to Earth. What about the change in momentum in an inelastic collision? Yep, 0. Momentum is conserved in collisions. That's the whole point of using conservation of momentum here. What about the change in kinetic energy in an inelastic collision? Does kinetic energy go up, down, or stay the same in an inelastic collision? Um, so, Joseph, momentum is conserved in all collisions. Yes, Grace, momentum is conserved in inelastic collisions. Um, Kinetic energy is not conserved. Is it? Can it be gained? And people are telling me no, and that's right. In an inelastic collision, two things stick together, and by sticking together, some of their initial kinetic energy is converted into heat or sound or something like that. One way to think of it is if I have two objects that are moving toward each other, and they collide and stick together, they have lost all of their kinetic energy. So inelastic collisions lose energy always. I can't gain energy just by throwing two things together, right? If I could come up with more energy than I started with just by throwing a wet paper towel against a wall, then we would solve all of the world's energy problems. So, are there any questions about any of these that we just did? Okay, let's move on to the next set. So here we have a whole set of questions about kinematics, about throwing something, shooting something over a building. So here, we're at an angle theta above the horizontal. And I'm not going to talk through all of these, but we know that the initial velocity in x is going to be v naught cosine theta. Our initial velocity in y is v naught sine theta. So let's just kind of look through these and quickly cross off the ones that aren't right. So we know this is not right away. No x and y components of the initial velocity vector. That's pretty easy. This one, let's see. X is right, y is right, vx is right, vy is right. This is the correct one. We can talk quickly about why all the others are wrong. So here I have flipped sine and cosine. So here are the x and y components are reversed. Here, I've got gravity acting in both x and y. And here, both of those are messed up. So that's pretty straightforward. Let's talk through the rest of this set, though. So, which question would allow you to determine whether the arrow strikes the left side of the building? So here we're choosing the point where the arrow is released as the origin. And we want to know whether the arrow hits the left side of the building, like that, whether it flies over, or whether it hits the ground. Isn't it in C where they are both messed up? So in C, yes, both x and y components are messed up. So I flipped both x and y. In D, what I have done, actually, yeah, D is the one where both of them are messed up. Yep. And that. Yep, you're right. Folks, I've just had a small tech glitch that will take me just one moment to fix. This will take 15 seconds for me to fix. I have a loose connection that connects my laptop.
The monitors that I'm using, and it has
folks, actually that didn't, what I just did didn't fix it. I may need to actually, so folks, I'm going to have to disconnect the docking station that has my headset on it for about 10 seconds. I will be right back. Sorry about the tech trouble. All right, we are almost back. You all can likely hear me, but I can't see anything that you're typing in chat. So give me just one more moment. I am so sorry. Okay. Now we are back. Sorry about that. Okay. So yeah, what you were telling me when my monitors went out. were that here, um, and coordinates reversed, and that here we have the coordinates reversed. Okay. Where were we? Where we were was in thinking about what question would let you figure out at what time the arrow hits the building. Um, so I will scroll back up to this and let you all ponder that. Kalhaku, did you mean to turn your mic on? To folks watching on YouTube, my apologies for any visual glitches that you will have had during all this. So, how do we know if the arrow hits the left-hand side of the building? Well, um, oh, can you all not hear me? Crap. Hmm. Folks on YouTube, I'm sorry about all this issue. Can you all hear me now? Can you all hear me now? Yeah, okay. This was actually, I'm not going to blame my setup for this. I'm going to blame Collaborate. This was a Blackboard Collaborate problem. Um, it turns out Blackboard Collaborate is very confused when you switch hardware in the middle of something. I had to rejoin the Collaborate session to get this to work. So let me reload my tool here. I was like asking you all to um, comment on something. I'm like, wow, the students are being quiet. Uh, yeah. So here we're asking, now that you all can hear me, what question you have to ask in order to determine whether the arrow hits the left side of the building. So to determine whether the arrow travels over the building, whether it strikes the left-hand side of the building, or whether it doesn't go far enough. So how do you know which one that is? So big A, again, is the distance to the building. So which one of these is it? Choice D. So we've got votes for choice D and choice C. So choice C is the most obvious one. We're simply asking at the time when the horizontal position is equal to the side of the building. So this here, this line that I'm drawing in blue is x equals a, and we're simply asking how high the arrow is up off the ground. If we get a negative answer, then it has, if the ground weren't there, it would have gone through the ground already. If we get a positive answer, then it's above the ground, and if we get an answer above h, then it's gone over the building. So this one obviously works. Are there any others? So both A and B don't work. We talked at length about why they don't work. Beginning of class, the short version is Our x velocity equation, remember, is just Vx equals V naught cosine theta. There's no acceleration in the x direction. The only way we have to calculate anything is to use constant acceleration kinematics. And if we say, oh, when the arrow strikes the building, um, it will stop. Well, at that point, we're no longer in the constant acceleration regime. So that doesn't work. But D and E are interesting. We're asking, what is the value of x at the first and second times x equals h? And you might be tempted to say, oh, well, if I have some kind of parabola, right, D maybe not because parabola. Yeah, yeah. So with a parabola, right, there are two different times that y is equal to h. And we could have a trajectory like this that strikes the building on the way up, but will continue to go upward. So here we figured out x the first time that y equals h. We could also have a trajectory that goes up like that. And, let's compare these. So we could have a trajectory where this is the first time x equals h and it hits the side of the building. We could have another one that goes like this, where this is the first time x equals h and it hits the ground. So because this trajectory is a parabola, and parabolas can be, a little bit complicated, it turns out you can't answer this question strictly by looking at the times y equals h. So we have to think about it a little harder. But choice C is the obvious one, right? We're saying there's only one time that x is going to be equal to a. X is going to be v naught cosine theta times t. So we figure out the time that equals a, and then we see how high it is. Question 5. If you ask the question, what is the value of x at the time that y is equal to h? So these two questions here for parts D and E, you'll get two results, x1 and x2, where x is the smaller one. What must be true about these two results for the arrow to land on the top of the building? So these next two questions, or this question is quite subtle. This is a difficult question. So here is the building, and our trajectory for it to land on top of the building is going to look like this. And our two values of x, x1, and x2. So what must be true about x1 and x2 for the arrow to land on top of the building? Again, this equals, this is where x equals a, this is where x is a plus l. So what's the answer here? Um, choice B. Yeah. Actually, this is not quite written right. This really should be, there's a typo in this question. This really should be x2 is greater than a, but x2 is less than a plus l. Because it's got to at least go to the building, right? So this is actually a kind of screwed up question. I messed up here, but that's the closest to the right answer. If x1 is greater than a, then that means that it's going to hit the left side of the building. If x2 is greater than a plus l, that means it flies over the building. So B is the closest to correct with my mistake. Tell me about number 6. Suppose you try to solve for the time that y equals h and get an imaginary answer, so the square root of a negative. What does that mean? C. Yep. It means the arrow will never make it to that height. So we did a lot of this. If you remember the frog catching the spider in the elevator problem, I know that seems like a decade ago now, but yeah, this is where you have some line and a parabola that never intersects it. So any questions about any of the multiple choice? We have some more. Those were the multiple choice that I wrote. Now we have some that Professor Rudolph wrote. Um, So here you've got an awning of mass M attached to a hinge on the wall with a wire holding it horizontal. The wire attaches at an angle theta with the awning. What's the tension in the wire? So this is a classic static equilibrium problem. Um, so like in all of these, you are going to calculate a sum of torques. First, we need an extended free body diagram. So I've got sorry, I palmed my touchpad here. I have a force here, so this is the tension force. I also have a force due to gravity here that's the weight from the beam. So to calculate the tension in the wire, I just calculate the sum of the torques around some point and set it to 0. Now there's also going to be some force here at the hinge, but we will choose our pivot here, so that one applies no torque. Right? So in this case, the sum of the torques is 0, so that means, so let's see, gravity is going to apply minus mgl over 2. Why is it 0? Because it's being held still, Grace, so it's not falling. Remember that the sum of the torques equals I alpha. So if it's not moving, alpha equals 0, and that implies that the sum of the torques equals 0. So minus mgl over 2, that's the torque from gravity. The torque from tension, this is going to be plus TL sine theta. That's the angle between them. So that makes the answer here C. I'm going to speed up a little bit as I go through these, um, just so we have like time to do some other things. But if you have questions, please type them in chat, and I'll answer them. Question 8. So an astronaut is floating in deep space with no forces. She's at rest. Somebody throws something past her, and she reaches her arm out to the side and catches it. After she does, what happens? So choice A, like clearly we know that's not going to happen, right? So this is a collision. Collisions conserve momentum, and this violates conservation of momentum. But it also violates conservation of angular momentum. Remember that if I have an object that can rotate, something moving past it has an angular momentum mv/r perpendicular. So the insight here is that this piece of equipment has both ordinary momentum and angular momentum if you're looking at angular momentum around the center of the astronaut. So choice A violates both conservation of momentum and conservation of angular momentum. So choice A is wrong. Choice B So choice B has her move, but it violates conservation of angular momentum. You might think like if I reach out my hand to the side and catch something, that's going to make me start spinning. So this violates conservation of angular momentum. This one, so where she just rotates, that violates conservation of ordinary momentum, right? So when she catches the thing, um, you know, conservation of momentum says that she must begin moving, and conservation of angular momentum says she must start spinning. So Joseph, what do you mean by look at it logically? You probably can, whatever approach you're thinking of, but I'd like to know that approach. Yes. So Joseph, what you're doing is very, very good. Joseph, can I ask your major? Um, and I'm asking your major to kind of connect to something. Yeah, aerospace engineering. So what you have just done is you have said, I've built up this intuition about how the physical world works, and I know things about how stuff moves. Um, and physics that doesn't describe how the real world works obviously is not the right physics. So when you're taking the exam, when you're doing physics, you can and should always use your intuition about how the objects around you move in order to figure things out. But um, the reason that I'm kind of going through this and talking through this one by one is if someone doesn't have that intuition, they'll need to like think back to the formalism from our class. Um, but what you're doing is you're saying, all right, let me imagine somebody sticking their arm out and catching something. They get knocked backwards and they get spun around. So yes, if you have that intuition, then please use it, right? That's the easiest way to figure this out. Um, so problem number 9, this is a toughie, but this is a demo we did in class. Um, you've got a toy car with a ball launcher on top of it, which shoots a ping pong ball straight up into the air. We know if it's rolling on flat ground, the ball will land back in the launcher. But if it's rolling down a hill when the ball is fired, where will the ball land? Um, so this is tough. I've got a car here. It's moving down the ramp, but when it shoots the ball, rather than shooting it straight up, obviously if we shoot it straight up, something different will happen, but we're shooting it at this angle here. And we're trying to figure out whether it lands back in the car or not. Um, so the easy way to do this problem is to remember the demo we did in class. We often like to ask questions that, on exams that are like, do you remember this demo we did in class? Or can you think through how it works? And it landed in the car. But to figure out why, the um, the easiest way to do this is to imagine a tilted coordinate system like this. And in this case, remember that the acceleration of gravity in x is g sine theta. You can just say ax here. And this is the same acceleration in x for both the car and the ball. So both of them have the same acceleration in x, so both of them are going to have the same x coordinate as a function of time. That one's a little bit tricky to know that you need to think that way unless you remember what we did in class. Do you still do demos in Physics 2? Yes, you do, and they are even cooler. In Physics 2 is all about electricity and magnetism. So you will do things like levitate rings using magnetism. You will do things like um, supercool an object with liquid nitrogen and see that magnets float in a really strange way. Um, Actually, not even magnets, that a metal object will float um, when it's supercooled. You will see other things having to do with electricity. I'm not sure exactly what they are. I haven't taught physics to, but you may do even really cool things with you know arcs of electricity, Van der Graaf generator, and somebody's hair standing on end. Um, I don't know if the person who teaches physics 2 has as much hair as I do, but surely there'll be a student volunteer. So yeah, the physics 2 demos are really cool. Um, all right, we got three balls rolling down three tracks. So first we're asking which one gets to the end of the track first. And what we know, right? We know that at any point, the kinetic energy is proportional to, or is equal to, mg times the distance moved down. So we know that for the first one, so here we're going slow, here we're going fast, here we're going slow, here we're going fast, here we're going slow, and here we're going fast, right? But in the middle is where things are different. In this one, since the dip happens in the beginning, we're going pretty fast in the middle. In this one, we're going pretty slow in the middle. And in this one, we're going pretty average in the middle. So, which one gets to the end of the track first? You all tell me. A, B, or C? A. Yep. Because it spent more time going fast. Now for problem 11, which one has the highest speed at the end? D. Yep. Because as you know, energy is conserved. They've both converted the same amount of gravitational potential energy into kinetic energy. So here we come to the end of the multiple choice questions. We could either continue doing the rest of this, in which case I'll continue recording and put this up on YouTube, um, or we could do something else. So what do you all want to do? You had a quick question about something else. Sure, Sam, what is it? Feel free to turn on your microphone and say what it is.
Hey, can you hear me?
I can hear you.
All right. Yeah, it was kind of a long message, so that I would just say it. So like I know we talked about the relationship between the linear acceleration and the angular acceleration for the spool that was like just rolling on a table.
Hmm.
But I was wondering how it would be different if the spool was like falling instead of just rolling on a table,
Do you mean
if
like
that makes sense.
the yo-yo problem that we did in recitation?
Yeah.
Yeah. So and by the way, it's great to hear your voice. And you all feel free to turn on your microphones and talk to me anytime you want. Um, so for the yo-yo problem, I'm gonna load that. Well, we'll just do it with a spool for now. There's no need to. Whoop, that's not what I wanted. I want another page, and then this one I want a plain background on. So here you've got a spool full of thread. Doot, 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 doot. I'll do it a straight line. And we've got a spool here that's got red string wrapped around it. So as this thing falls, it spins. So this is going to move down. So the linear acceleration is down. And the angular acceleration, is it going to go clockwise or counterclockwise?
It'd go counterclockwise, right?
It'd go counterclockwise, yep. So what you know here, again, is that this point of the string is not moving. Or another way to see it is that, and this is maybe more intuitive, that this thing has to unroll 1 inch of string for every inch that it falls, right?
Mm-hmm.
So let's write this in words here. For every inch fallen. So unrolling string, that tells you about its rotational motion, right?
Mm-hmm.
So I'll say the tangential rotational motion of the edge of the spool. But this tells you about translation. So what that means is that the tangential motion, you know, is omega r, right?
Yeah.
That's how fast a point on the edge is moving, how fast it's unrolling string. And this has to equal to the magnitude of the velocity. Now, this is plus or minus because all that we don't know whether it's unrolling string by turning in the positive or negative direction. So, which rotational direction do you want to consider positive? Clockwise or counterclockwise?
Uh, Counterclockwise.
All right, so you want to consider this to be positive for rotation. Which translational direction do you want to consider positive, up or down?
I guess down.
Okay, so that's positive. So do omega r and v, do they have the same sign or opposite signs?
They'd have the same sign.
Yes, with his coordinate system, they have the same sign. But if I put the string on the other side, or if I chose a different coordinate system, that might be minus. You have to think about this every time. So this one is plus. These have the same sign. And the derivative of this is um, alpha r equals a, which you'll then need to use in Newton's laws to solve the problem. Does that answer your question?
Yeah, and then if you just like if it was like the if you moved the point closer to the radius, would it still be the same or would that then change it because the acceleration is changing?
Great question. So now you're thinking about the yo-yo problem. What if we, didn't mean to erase all of that. Um, what if we took this and you want to now, well, we'll erase the whole thing. You want to now connect the string closer into the inside, where now the string is wrapped around like this and goes up there, right?
Yeah.
So now we've got, so this is the yo-yo. Get rid of all that. Boop. So now we've got two radii. We have the smaller one, which I'll label as little r, and we have the bigger one, which I'll label as big R. So suppose this is the yo-yo problem that you did earlier. So in this case, which radius determines the rate at which it unrolls string?
Little r.
Little r. Which radius is the one that determines how hard this is to rotate?
Big R.
Yep. Um, For the folks on YouTube, let me just write this out. So that's the rate of unrolling string, and then big R is um, determines how hard it is to turn. So which one of those is relevant for omega equals, or excuse me, V equals omega R?
Um,
Little r or big R?
would it be little r?
Little r, because that's the one the string is unrolling from, right? Which one
Okay,
determines the moment of inertia?
big R.
Big R. Yep. So if this is a yo-yo where we're treating the slot as small, then this is big R squared. Does that make sense?
Yeah.
Yeah. These problems where you're combining rotation and translation of stuff, um, often students find those to be among the most challenging in Physics 211. Not because the math is hard, but because you have to think clearly about this kind of thing.
Okay.
I,
Um, who had a question?
I have a question. Because this was on one of our recitation packets, right?
Yep.
I think, does it depend where the mass is all centered in the object when you're choosing what to use for the moment of inertia?
Yes. Yes, it does. So remember the moment of inertia, the formula for it is m times the average value of r squared, where those brackets mean average. And
Okay.
um, ordinarily taking that average is hard and requires calculus. That's why we give you those fractions. But,
Uh-huh.
if I had a yo-yo where, more of the mass was on the inside than the outside, it was unevenly arranged, that shape wouldn't be in your table. Like you couldn't figure out the moment of inertia in any easy way.
Mm-hmm.
So what we did for our problem, just so you could figure out the moment of inertia, was we said it's you can think of it as a uniform cylinder that a really thin slit has been cut in. Um, but if it's some other, shape, maybe you have a ball that's, made out of lead on the outside and steel on the inside. I don't know. Um, then the moment of inertia gets hard, and we're not going to do that. Does it answer your
Okay,
question?
thank you.
Sure.
Yeah.
Thank you for being brave enough to talk. I miss hearing your
Yeah, I have
voices.
to go, Professor, but thank you for doing the review sessions. They're really helpful, especially like right before the test.
Of course, Samuel. I really appreciate all of your enthusiasm and all of your hard work. And thank you so much for bearing with our class. Even as the end of the semester has gotten crazy.
Yeah, of course. You make it easier for like among other professors too.
Thanks. Yeah, we try. We try. Anything else that anyone wants to talk about? Can you go over question one? So you want to just do the rest of the this thing? Yeah, we can do that. So this is actually a very similar question. Sure, Martina, and that's actually great because then I can just post this on YouTube and I don't have to record it separately. I'm running out of time to do all of the things that I need to do before the exam because there's only one of me and a lot of stuff to do. Um, so here is Bruin. Bruin is a very very good boy. He apparently has his own Instagram channel. Shannon tells me. So this problem is actually really similar to the one we just did, except rather than you can think of a yo-yo as being pulled down by gravity and um, being constrained to roll along its string, right? It's kind of a weird way to think that like if I drop a yo-yo, it's rolling along its string, but that's what's going on. So in this problem, rather than a spool falling down and being pulled down by gravity and rolling along its string, here it is um, being pulled not down but sideways by this friendly dog, and it is rolling along the ground. So it turns out that this problem will be really, really similar to what we just did. except here we're going to do the algebra. Um, so let's draw the extended free body diagram here. So Bruin is pulling this truck wheel. So we got to draw the ground here. Let's see, here's the ground. Um, there we go. So what forces act on the wheel? Well, so the rope is attached to the axle of the wheel. So it's attached here to the middle. I don't think I want an arrow that's quite that fat. So that's the tension. There's also a force from friction. So the frictional force is right at the ground. And it goes straight to the left. So, first question. So suppose Bruin pulls with some tension, and it's not very big. So the thing rolls without slipping. How big is the force of friction? So we've kind of got four choices. I'll label them A, B, C, and D. And I'm actually going to use the little poll thing. Oh, I can't do a poll and still share this at the same time. Yes, I can. Yes, I can. So we're going to have you all vote on whether it's A, B, C, or D. So I'll wait a bit. I should probably say something so the people watching on YouTube are not completely bored stiffless or senseless. So here we have to decide whether it is static or kinetic friction, right? So choice A is kinetic friction, choice B is static friction. Choice C says, oh, there's no friction at all. And choice D is something else. So what I'll remind you is that choice B here, this is the maximum value of static friction. It doesn't need to necessarily be that big. Remember, mu SMG is just the biggest static friction could be. So I'll give you all just a few more seconds to get your answers in. So the majority vote is B. Most people are saying it is static friction at its maximum value. I'm not going to try to ask who was who, but the correct answer here is D. Only one person got this. This is tough. Because suppose that Bruin is pulling something very, very heavy. And Bruin pulls with only like a few pounds of force. Well, because the tension is small. So if he's pulling with only a few pounds of force, static friction is not going to be like 100 pounds. Static friction will be some smaller value, just whatever's needed to keep it rolling without slipping. You know it cannot be A because it rolls without slipping. So this means static friction. And you also know it can't be zero because if there were no friction, then there would be no torque and the thing wouldn't spin. Um, so when we say rolling friction, what we mean is, so imagine that you had a bicycle and you rode your bicycle somewhere with no air. Um, so you took away air resistance and you ride a bicycle over flat ground. Um, your bicycle wouldn't keep rolling forever. It would gradually slow down because you would lose some energy in the flexing of the wheel, um, and going over a bumpy surface. So rolling friction refers to the energy that's lost, um, as a rolling object deforms very slightly as it rolls over the surface. But rolling friction is usually really small. So coefficients of rolling friction are 10 to 100 times smaller, or even more, than coefficients of static and kinetic friction. So generally in this class, we have treated objects that roll as, okay, we need to think about static friction, um, because the static friction is what keeps the tire from slipping on the pavement, but it you don't have any extra rolling friction that dissipates energy. So rolling friction is like an extra thing that sucks energy out of the system. So we don't really do rolling friction in this class. It's not terribly interesting. Good. All right, we need to get that out of the way. Um, so I guess we already drew a force diagram, didn't we? Um, so here we'll choose the pivot to be at the center. So here, the torque due to tension is just 0 because it acts at the pivot. And the torque due to friction, um, do we want clockwise or counterclockwise to be positive? Counterclockwise, okay. That's the convention. So this force, the force of friction makes it go clockwise, right? So this would be minus F fric times the radius of the wheel. Okay. Question C says, without doing any math and looking only at your force diagram, is the acceleration equal to, less than, or bigger than t over m? So we want to compare the acceleration to t over m. So you tell me, is the acceleration more than, the same, or less than t over m? Less. Yep, because you've got another force going to the left, right? So if you had F equals sum of forces equals ma, then you'd have tension minus F fric equals ma, right? So less than, there's another force going left. Okay, write down an equation relating the forces on the wheel to its acceleration. Hey, we just did that. T minus F fric equals ma. Write down an equation relating the forces on the wheel to its angular acceleration. So this is, we're looking for angular acceleration. So now we have the net torque equals I alpha. Here, I'm just erasing because I want to color code these things. So the net torque equals I alpha. Okay, so the torque here we decided was minus F fric times radius. Sure, Grace, let me write this equation here, and then I will certainly do that. The moment of inertia is 1/2 mr squared times alpha. So why is the torque caused by tension 0? Remember that, and I'm just going to write up here by the force diagram, remember that torque is the perpendicular component of the force times the radius. But this radius, this means the distance from the pivot to the point of force, right? And at this point, the pivot here is in the middle because we chose it to be there. And that's the same place that the tension is acting. So in this case, this radius is 0 for the tension. Does that clarify that? Good, good. Okay. So now we have this. And I can notice, we can clean this up a little bit. We notice that one radius cancels from everywhere. So we get minus, just going to move it over, minus f fric times the radius that we canceled equals 1/2 mr alpha. Okay, and now we're supposed to figure out the acceleration of the wheel. So let me write down the two equations I have. I know that minus f fric equals 1/2 mr alpha, and t minus f fric equals ma. So this, though, is a problem with two equations and three unknowns. We don't know the angular acceleration, we don't know the linear acceleration, and we also don't know the force of friction. Remember, we saw in part A that the force of friction is not mu mg, it's something else. So what do we do here? I've got two equations and three unknowns. How do I make progress? Think back to the yo-yo problem. Yep, I need the relationship between alpha and A. So I have, because we know this rolls without slipping, the no slip condition is that alpha r is plus or minus A. So is it plus or is it minus? Yes, Grace, that's right in magnitudes. But we have to think about the sign. So with the coordinate system you have chosen, is this wheel going to move in the positive or negative direction? We chose this to be positive. So are we moving in the positive or negative direction? We're turning in the negative direction, Lisa. So yes, we've got translational motion and rotational motion. So as Lisa points out, we are rotating that way, but we are moving that way. So looking at the diagram and thinking about how we're moving, we are translating to the right, which is positive, but rotating clockwise, which is negative. So these two are opposite signs. So this means that alpha r equals minus A. So there's something I want to say, a bit of a digression here. Some of you may have already heard me say this in the other review. So I was really far behind in mathematics when I entered grad school. And one of the things that Like I really had to kind of find other ways to do physics while my mathematical knowledge caught up. And one of the things that I only very late in my life realized, it's kind of embarrassing, is that when you do substitution, you can substitute in more than one variable at once. So you might say, all right, here, let me solve for alpha and plug in alpha. But I can do better than that. I can say, okay, I know alpha times r, and I have a formula for alpha times r. So I can plug in for both of those variables at once. That can make your life a lot easier. Another way this comes up is if you're dealing with conservation of energy. Often, rather than like solving for v and plugging it in to kinetic energy, it's easier to solve for v squared and plug that in. Often it's easier to get a formula for v squared. And if you solve for v, you'll just wind up taking a square root that you'll just undo later. So if I substitute that in, this becomes minus f fric equals 1/2 minus 1/2 ma, right? So the force of friction is just 1/2 ma. Um, have I done that right? Yes, yes I have. And then if I were to substitute that in here, I would have T minus 1/2 ma equals ma. So A here would be 2/3 T over m. Any questions about how we did that? So the steps were, I know this object both rotates and translates, so let me write down F equals ma to understand its translational motion, torque equals I alpha to understand its rotational motion, and then I observe that it rolls without slipping, and since it rolls without slipping, I have a condition that relates angular and linear acceleration. So does that clarify this problem for everybody? Lisa, you were the one who asked to do it. So does that answer your question here? Good. I can tell you there will be a problem like this on the final. It's not going to be this problem. It's not going to be the yo-yo problem. But all of these ideas that we just used right here will be on the final. So look out for that. I've already written that problem. I wrote it last night. We're writing a few more problems tomorrow. Would you all like to continue talking about this, or would you like to do something else? We can continue like through this if you'd like, or if there are any other topics people want to review, we can do them. Okay. I did this problem in the review yesterday, but that's fine. We can do it again. Actually, was there anybody here who was in the review yesterday and has already seen this problem? Because what I can do is I can like do those last. Yeah. So let's skip this one, and we'll come back to it at the end, because you've already seen this. All right. Yeah, that's right. You and Grace were there, Avery. So here we have a problem. A string is attached to something, and a thing is hanging from the bottom. So here we've got a ceiling. Let's see, here it is. Doop. Nope, I don't want my highlighter. So here's the ceiling. We have a spring hanging from it, and we attach some mass m to that. So there are two ideas that you need in this problem. So the first one is that the spring force is minus K times the change in stretch amount. The minus sign just tells you that the spring pulls in the opposite direction that it has been stretched or compressed. The other one is that the spring energy is 1/2 K times delta x squared. And the difficulty in this problem, it's not terribly difficult, but you need to make sure you're clear on when force is the thing you should think about and when energy is the thing you should think about. So in part A, should we be worried about the spring force or the spring's stored energy? Okay, Martinez says energy. Any other votes? Okay. Um, 3 votes for force. So could somebody either turn on their mic and tell me or type out why you want to use force? It turns out it is force, but tell me why. The force equation contains dx and isn't as complicated? Okay.
If it's at an equilibrium, then the acceleration is 0, so you can just set like the two forces involved are gravity and the spring force, so both of them have to result in an acceleration of 0.
Yeah, exactly. So here, um, this is not, so we're hanging. That means A equals 0, right? So um, since A equals 0, that means the net force is 0. So if I think about the force diagram, right, weight goes down. Yeah, it's not the best force diagram I've ever drawn. Let's see. Elastic force goes up, weight goes down. So this tells me that the elastic force, which is K delta x minus mg, equals 0. I can't use energy here. I know that because using conservation of energy um, requires you to have a before and an after picture, right? You're relating the energy in at one point to the energy at another point. And you don't have that here. You just have a thing hanging. So at this point, what you've got, let me just going to write this on the left so we have more room. K delta x minus mg equals 0. So delta x equals mg over k. All right. So the mass is 2 kilograms. G is 10 meters per second squared. The spring constant, is 200 newtons per meter. So looking at the units, in the numerator, that's newtons, and the denominator is newtons per meter. So this gives me 0.1 meter. All right, so now in part B, we add another mass let's doodle this out. Well, we'll doodle it this way. So first, it's hanging like this. And then now we add another mass. And that makes it go down. And there's a hint for this in part C, that here the masses are bouncing up and down for a while. So in part B of this question, what technique do we use? Force or energy? Yeah, energy. Because here we've got a clear before and after picture. So here I can say, so we'll choose this point. We don't know where the bottom is yet. When we're thinking of gravitational potential energy, we'll choose that as y equals 0. Actually, no. We'll choose something even easier. That way, our life gets hard, or our life gets easy. I'm going to choose up here at the equilibrium height of the spring as y equals 0. So this is equilibrium position of the spring. So by making that choice, that means I can use the same variable for height and for like spring stretch. So what do I have? There are no other, non-conservative forces here. So I can say the initial kinetic energy plus the initial potential energy in the spring plus the initial potential energy from gravity equals the final version of all of these. Now, this is asking how far do the masses fall in total? So we want to know like that distance. But tell me about these terms that I've written down. Do I know any of those? Initial kinetic energy is 0. Yep. Is anything else here 0? There's one other term that is 0. So what we're asking is the furthest point downward that this thing goes, right? So it falls down to here, and then it goes back up. Yeah, exactly, Ryan. The final kinetic energy is also 0, because that's the lowest point where it has stopped moving and is about to come back up. So I'm going to need some more room, just because a tablet is harder to write small on. I'm going to need some more room to solve this algebra. So I'm going to erase my picture, but I'm going to keep that equation. So I have, actually I will draw my picture again because this is important. So I'm going from here down to here. Here is my ceiling. There's my mass. Here's my mass. And there is my initial height. And just to make my life super easy, I'm going to choose down to be positive. Actually, no, I'm going to take, how do I want to do this? Yeah, we'll choose up to be positive still. Um, so we have added the mass already. It turns out that I have to do work on this mass to get it up there and hook it on. And the issue is that the reason it falls is once I have attached this other mass to it, I'm giving it extra gravitational potential energy. So yes, as the thing falls, gravity is doing work on both of those masses. So we now have that formula over there. So let's write that down. The initial potential energy of the spring plus the initial potential energy of gravity equals their sum in the end. Final spring plus potential energy final gravity. Okay, so now I just need to put in expressions for these. I'm going to call this y initial. I have an expression for it up above. I'll put that in at the end. And I'm going to call this y final, which is what we're trying to solve for. So potential energy in the beginning, let's see. So this is going to be, notice that all of these y's are going to be negative, right? Because the thing is moving downward. That's fine. So remember when we talked about negative potential energy? Here we go. I've set up a situation where I have negative potential energy. Oh, that's the gravitational one. So that's plus mg y initial. The potential energy in the spring is 1/2 k y initial squared. And then the final potential energy in the spring, same formula, 1/2 k y final squared. Oops, that's 2m plus 2mg y final. So that's my energy equation. Is everybody clear on how I got to this point? Yeah, this problem, actually, we usually put this on, so this was on a group exam last year or 2 years ago or something. This is a tough problem because it's easy to kind of tangle yourself up in algebra, but the key insight we're looking for is that in this part you have to use energy. So now it turns out that we know y initial, right? We know y initial is mg over k. So we know y initial is minus mg over k. So what I'm going to do, this initially looks like it may be a messy quadratic formula thing. We'll see in the end that it isn't, that this actually is something you can factor without using the quadratic formula. At least if I'm remembering how it goes correctly. So let's put this in. So I have 1/2 k times y initial squared. So that's going to be times m squared g squared over k squared plus 2mg times that. So 2, oh, but it's minus, right? Because y initial is negative. So 2mg times mg over k equals, on the right-hand side, 1/2 ky final squared plus 2mg y final. So now we notice that the left-hand side simplifies. I have, so on the left-hand side, right, I can right away, or the left term, I can cross out those k's, and I can combine the mg's. So this whole thing on the left-hand side turns into minus 3/2 m squared g squared over k. And this is equal to 1/2 k y final squared plus 2mg y final. Now, at this point, you might be tempted to say, well, okay, this is a quadratic equation. Yes, Martina. So we've chosen a coordinate system where up is positive, but where everything hangs below the y equals 0 point. So yeah, I mean, you have to choose up as positive for potential energy. Yes, exactly. So at this point, you could just use the quadratic formula, and I wouldn't blame you if you did. But we can actually be a little bit clever here. So what I'm going to do, I'm going to write this down because this is a bit tricky. And so folks, I am not expecting any, you all are early career undergrads, right? I'm not expecting any of you to just see that this is the right thing to do. This is one of, like, the only reason I know to do this is experience. You might be tempted to say, okay, let me treat this as a quadratic in y final. But one of the things that you can do with the quadratic formula is you can have combinations of variables as the thing you are solving for. So I'm going to multiply by 2k. So what does this give me? This gives me minus 3 is this what I want to do? Yes. So this gives me minus 3 mg squared equals k squared, or, well, I'll write it this way. K times y final squared. And here I've multiplied by 2k, so plus 4 mg, let me do something suggestive with my colors, for mg k y final. So everybody agrees I can do that, right? So now what I'm going to do is put all of the terms on one side. So this gives me 0 equals k y final squared plus 4 mg Ky final plus 3 mg squared. So this is kind of a digression. I'm not expecting you to learn any physics from this, but the algebra pattern you are seeing here will be very, very useful to you in the future. Notice that what I've done is I've rearranged this to kind of look like a quadratic equation or a factorable thing where the variables here are ky final and mg, right? So this kind of looks like 0 equals x squared plus 4xy plus 3y squared. Right? You sort of see how that's the pattern of this expression. And what could you do to that expression? So think back to your Algebra 2 classes in high school. I know this is like the most boring part of physics. What could you do algebraically to that to make it simpler, to maybe figure out what x and y could be? Yeah, Ryan, that factors. Exactly. So remember when you're factoring these sorts of things, you need, if you have a 1 in the front, you need two numbers that multiply together to give you the last coefficient, but that add together to give you the middle coefficient. Um, so, so if you factor this, this gives you 0 equals ky final um, plus 3mg times ky final plus 1 mg. And that means that ky final equals either minus mg or minus 3mg, and that means that y final, the thing we came here to find, is equal to either minus mg over k or minus 3 mg over k. Well, which one is it, right? We got two answers. Which one is the one that it will fall to? This is a surprisingly difficult problem because of the algebra here. Yeah, it's 3. What does the first answer? What is this one that I'm underlining? What does it represent? Yeah, that's just where it started, right? We did that a bit ago. We found that the initial height we put in here, right? So what we've learned is that this distance is mg over k, and that distance is 3 mg over k, and both of those are the points where it has no kinetic energy. Remember, what we put into our equations is tell me where it has no kinetic energy, and you know, there are two places where it has no kinetic energy, so you shouldn't be surprised that you got two answers. Did everybody follow me through that sort of gross algebra? Because the algebra is useful to see, right? The fact that you can use the quadratic formula on things that have variables in them, or maybe factor them. This is really just the quadratic formula with coefficients 1, 4, and 3. And we could factor that rather than going through the quadratic formula. But the physics, the thing that I really want you to take away from this is to know that this is conservation of energy. So let's move on to question C. So question C says that after this thing bounces up and down for a long time, it'll eventually come to rest at some point, hanging there at some other distance below equilibrium. I'll call this y3 equals question mark. So how do I do part C? Same as A with, yeah, exactly. So Grace, um, recognizing patterns, recognizing, hey, I've seen this before, intuition like that, that is what skill in physics is about. Yeah, this is just A with a different mass. So I take this and I put in 2m. So this is now y3 is minus 2m g over k. Nothing even to talk about. So this problem was not very, it didn't look tough, but recognizing that parts A and C make you think about force from the spring, and part B has you think about spring potential energy, that is definitely a subtlety about this problem. And, you know, it shouldn't be a surprise. First of all, our answers to parts B and C shouldn't surprise us. So part B said it bounces back and forth between mg over k and 3mg over k. And then in part C, it comes to rest at the halfway point. That shouldn't surprise us. But this problem, I've assigned this problem for homework, and this has actually stumped a bunch of clinic TAs. Usually we like our TAs get heads up on this, but the TAs who don't work for Physics 211, they're PhD candidates, and this has stumped PhD candidates in the physics clinic. So if you did this problem on your own and said, this is tricky, yes, it is. You have to think very clearly. We did question 4 in the previous thing that some people were at. Let's talk about question 5. So here we've got a ball bearing rolling down a hill, rolling across the table, going thump on the floor. So what I'd like to do is I'd like to label 3 points here. Point A, point B, and point C, and we'll use those as subscripts. So how are we going to figure out how fast the ball is traveling at the edge of the table? So we're going from point A to finding the velocity at B. How are we going to figure that out? Energy. Yep. So what kinds of energy do I have at point A? Remember, we're going to say energy at A plus the work done by other forces in going from A to B equals the energy at B. So at point A, what sorts of energy do I have? Gravitational potential energy, and that's it. So as we saw in the last problem, we can choose our zero height for gravitational potential energy anywhere we like. In this problem, where would you like to choose as your zero height? at the table. Okay? So this will be y equals 0. So our potential energy at A, let's see, we have gravitational potential energy at A. We don't have any other forces doing work. We talked a bit ago about how, yes, there is static friction present when something rolls on a ramp, but that doesn't do any network. So there's none of this. What kinds of energy do we have at B? Kinetic energy. Okay. Tell me more about that kinetic energy. What kind of kinetic energy is it? Rotational and translational. So we have gravitational potential energy at A, and this is equal to the sum of rotational and translational energy at B. So the gravitational potential energy at A is just mgh because of the where you chose your coordinates, so that's going to be mgh. Rotational kinetic energy at B, that's going to be 1/2 I omega B squared, and the translational kinetic energy is going to be 1/2 mvb squared. Okay, what do I do now? I can put in my moment of inertia. While I'm doing that, think about what the next step should be. You have a question for H. What's your question, Lisa? Is it H plus R? That's a really good question. So if you want to kind of think about the nuances of this, we didn't expect you to go this in depth, but it turns out it is just H, because the ball here, right, it's going to be like that, and at the edge of the table, it's going to be a little bit above the table, but at the beginning, it's going to be a little bit above the ramp. So it turns out that that extra height equal to the radius of the ball, that cancels between the top and the bottom. Yeah, but you don't have to go that in depth. Often little balls are smaller than ramps, so that's fine. So the moment of inertia then is going to be 2/5 m r squared times omega b squared plus 1/2 mvb squared. And Dante has said that we now have a relationship between the angular velocity and the translational velocity because it's rolling without slipping. So we know omega equals v over r, or v equals omega r. We don't have to think about signs here because this is always squared. So that means that this stuff here is just v squared. So this becomes mgh equals 1/5, because I did 1/2 times 2/5, times v squared, well, mv squared, plus 1/2 mvb squared. I can cancel all the m's. That's nice. And I get that vb squared equals gh divided by, and I'm going to write this in kind of a funny way, 1/5 plus 1/2. So it's interesting, you have one term in the denominator that comes from the translational piece and one piece that comes from the rotational piece. You can even see that they're, you still have both terms separate. But ultimately, we'd like to simplify those fractions. So this gives us, so 1/5 plus 1/2 is 7/10. So this gives us that VB is equal to the square root of 7/10 GH. No, sorry, 10/7. So everybody clear on how we did that? That's kind of the classic thing rolls down ramp problem. But there's another piece too. This asks us, how fast is the ball traveling when it strikes the floor? So how are we going to figure out VC? What technique do we use for that? Any thoughts? Dante suggests using kinematics. Are there any other techniques you can use? Can you do the same thing again? Yes, you can. And so Dante, it turns out you have to use kinematics for how far past the edge of the table does the ball land. And you have to recognize that projectile motion requires this. But if we're asking about the velocity hitting the floor, we can do the same thing again. But what is this hint doing here? Hint, what happens to the ball's angular velocity as it travels through the air? Does it stop rotating, Nathaniel? Or does it do something else? When you say it's not rotating, you're very, very close to what happens. It turns out it doesn't change, right? If it, you can think of this as a conservation of angular momentum thing, or you can just use our intuition. Um, so the rolling without slipping condition is not true as the ball goes through the air, right? It's not rolling on anything anymore. So its linear velocity v is going to increase in magnitude as it falls, but its angular velocity is not going to change as it flies through the air. And that is something that can catch people. So yes, here we can use conservation of energy again. We know, so let's just write this down. The translational kinetic energy at B plus the rotational kinetic energy at B. Yes, exactly, Grace. Gravity makes it fall faster, but doesn't make it spin any faster. Gravity it does positive work on it translationally, but gravity does not apply a torque to it. So the big alarm bell is that one, that the rotational energy at B is the same as C, right? That is something that can catch people off guard. So let's just put in the stuff we know. The translational kinetic energy at B is going to be, we'll go back to colors here. So this is 1/2 VB squared. The rotational kinetic energy cancels, right? That's the same. You know, I'm kind of going through the formalism here, but the point is, as the thing falls, it's no energy is gained or lost from its rotation. Its rotational energy just stays there and cancels from both sides of the equation. Its potential energy, whoops, I forgot an M. Its potential energy at B is 0, right? Because you chose the edge of the table to be 0 height. So the translational kinetic energy at C, that's the thing we came here to find. Could drag force cause it to rotate while it was falling if it was in the problem? Ah, that is an amazing question, Nathaniel. I'm going to defer that. The answer is yes. I'm going to defer that question to the end of the problem because it's really cool. I'm actually going to show you a YouTube video after this. And the potential energy at C, so notice that we are going down here. So this is minus mg big H. Now, it turns out we know VB squared, right? VB squared is 7/10 GH. Or excuse me, 10/7 GH. We just figured that out. So, let's see. This is going to be 1/2 m times 10/7 GH equals 1/2 mvc squared minus mg big H. Okay, 1/2 times 10/7 is 5/7. So what this is telling me, bringing both terms to the left, is that 5/7 mg little h plus mg big H is 1/2, oops, mvc squared. All the masses cancel as before. We can multiply through by 2, and this gives us that Vc is the square root of 10/7 g little h plus 2g big H. So yeah, I can use conservation of energy. Works just fine. This doesn't tell me which direction it's traveling in, but it does tell me how fast. Okay, part C says how far past the edge of the table does the ball land? And for that, you just use kinematics. I'm going to do this one pretty quickly. I don't think we need a lot of review on this. So we're asking, what is x at the time y equals -h with your coordinate system where you choose the origin to be at the edge of the table. So that's your origin of coordinates. I know x of t is just going to be v naught t, and the initial velocity is this one we have found up here, right? That's the speed that it rolls off the table with. vbt, I'll plug in for that later. Y of t is going to be simply minus 1/2 gt squared. So if minus h equals minus 1/2 gt squared. Then t is equal to the square root of 2h over g. And that means x is equal to vb times the square root of 2h over g. Well, vb was the square root of 10/7 gh. So that's equal to square root 10/7 gh times the square root of 2h over g. Yes, you are right. Thank you. To big H over g. Yep, thank you so much, Grace. I was about to just completely bungle that. It's the problem with like speaking, because you say both of those letters in the same way. Now, you can combine these two. So if I multiply these two square roots together, this gives me 20 over 7, because 2 times 10 over 7, little h times big H. And this makes sense. It'll go further if the ramp is higher, but it'll also go further if the table is higher. So any questions about any of the physics that we just did? So I wanted to show you a YouTube video now. So I've got to share, let's see, how do I do this? Share, I don't want to share files. So the question was, that was asked a bit ago, was about could air drag apply a torque? Absolutely. This is something called the Magnus effect. And it turns out if you have a spinning object that's moving into the wind, there's going to be more drag on one side than the other, right? Because if I imagine like a ball that spins as it moves forward, one side, there's going to be extra drag because that side is rotating against the wind, and one side there's going to be less drag because that side is rotating kind of with the wind. And here is, you should be able to see like the beginning of a YouTube video. Is this the right one? Yeah.
We're here at the Gordon Dam, and what we're going to do is demonstrate from the very top the effect of spin on a ball. So we're going to get a basketball and drop it from 140 meters up, one without spin and one with spin, and see what happens. All right, you guys good down the bottom? Ready?
Did you drop a basketball and it goes down, right?
How's the curve? Slow, yeah. Yeah, so it's crazy, just dropping it with no spin or anything like that, and as you could see, you know, the ball was sort of doing a sway thing, so it wasn't going directly straight. It was pretty hard to predict where it was falling, so that was really cool. Ready? Whoa, look at that go!
To get back in the water, do you?
This is Brett who just threw
Yeah,
it.
yeah, that's pretty
I
impressive.
literally just dropped it with a bit of spin, like I didn't even throw it, and it just took off. Like we had no idea that was going to do that. But yes, in the water, please. So that was a pretty amazing experiment with some really interesting results. So the first one that we had no spin on, it dropped straight down with some lateral movement, quite a lot of lateral movement, as you would have seen. But it didn't actually go forward at all, so it was almost, you know, fell directly below where it was dropped, which is what you would expect. But the one where we added the backspin, it went perfectly straight, but it really took off as it gained speed, and it went, you know, close to 70 meters, I'd say, from the point at which we threw it, so 70 meters horizontally. So That was incredible. And as you can imagine, when you're doing a trick shot, all it does is highlight the complicated nature of the spin of the ball and how far it goes. If you put slightly less spin, it's going to go way shorter. If you add more, obviously it will go further. If you throw it without spin, then it's just going to fall straight down. Very interesting. We learned a lot. We were really impressed with the results, and we hope you were too. Our good mate Derek from Veritasium has done a really cool video which explains why the ball went so far with the backspin. Watch the video and then check out and subscribe to his channel.
Yeah, yeah. So yeah, that's a real thing. So if you have an object that is spinning as it moves through the air, and you think about air drag, you have unequal drag forces on the different sides of the object, and that can cause all kinds of stuff to happen. It can cause torques. So as you saw, the ball spun a little bit when it was dropped straight. This is the principle behind a knuckleball in an American baseball. So in baseball, there's someone who throws a ball and somebody tries to hit it with a bat, and the pitcher can do all kinds of crazy things because the ball has stitches on it that cause extra air drag. And if the pitcher doesn't put any spin on the ball at all, then it will start to rotate very slowly because of the torque from the drag from the stitches, and that'll cause it to dance around unpredictably. But if you put a lot of spin on the ball, then there will be more drag on one side than the other. And that will cause it to drift to the side. So yeah, spinning objects moving with air drag have crazy things happen. All right, so that's the end of that problem. Is there anything else people would like to talk about or see?
Yes, could we look at problem 1 on the finals problem?
Could you do so? This is the this problem here.
Yes.
So we did it a bit ago.
Yeah, I just joined, sorry.
Yeah, that's okay. So the video is going to be posted on YouTube. But I can talk through the basic approach to doing this problem. And then if you want the full solution, you can catch this on YouTube. What we did was we realized first that if Bruin pulls gently on this wheel, then the force of static friction is not necessarily going to be equal to its maximum value. It's going to be something less. And then we said, okay, as Bruin pulls on this ball, pulls on this wheel, there are going to be two forces, the force of tension that he's pulling with and the force of friction between the wheel and the ground. And those forces will do two things. They'll cause the wheel to move, give it an acceleration, and they'll also give it an angular acceleration. So we then wrote down Newton's second law for rotation, the one on the left, and Newton's second law for translational motion, the one on the right. And we realized that since the wheel doesn't slip, there's a relationship between how fast its center of mass accelerates and what its angular acceleration is. So we figured out the no-slip condition. It's alpha r equals a. But the a is plus or minus because that's just true for the magnitudes. So then we had to come down there and say, okay, what's the relationship between the direction it turns and the direction it moves? And we thought about that, and we realized that that needs to be a minus sign. Once we figured that out, then we have three equations and three unknowns. So we were able to take the torque equation for rotational motion and substitute in r alpha for a, and that gets us down to two equations that relate the tension, the force of friction, and the acceleration. So we solve for the force of friction, we plug it in there, and then we find the acceleration in terms of the tension and the mass. So that's the approach to that problem. Do you have any questions you'd like to ask online about it? Or does that clear up how to do it?
You said you'd post it on YouTube too, right?
Yeah. So the full solution from a bit ago is going to YouTube.
Okay, yeah, that helps. Thank you.
All right. Anything else anyone would like to talk about? You're all set. So before you head out, Martina, and it looks like there aren't going to be a lot of questions, um, the names that I see here are a lot of super devoted students this semester, devoted to learning. Pei, I know you are working super hard balancing being in the ROTC and actually are you green to gold? Pei, I remember you were some other officer candidate thing, if I'm remembering right. Ryan, I know you've been asking questions all semester about like literally everything. Avery and Grace, I know you have been working super hard. I have seen you all again and again and again in my office hours in the physics clinic, asking questions, making comments in class, getting great grades on exams. I would like to invite all of you to keep us in mind when you're looking for student employment. Um, if we hire coaches out of each year's class. So if you do pretty well in this class, pretty well is usually a B or better, um, and you feel like you have strong communication skills or you'd like to work on those, and you would like a job, you'd like to get paid to do the same things that you have seen the other coaches doing this year, um, possibly in the fall, but definitely in the spring when I'll be teaching the class again. I need good people as coaches. So those of you who enjoy this sort of thing and would enjoy a job teaching your classmates, um, please keep us in mind. Yeah, Martina, I know I've seen you uh, always in the clinic, always here. Um, and you've asked really, really good questions. Like, I remember how articulate you have always been. Like, I need help on this specific thing, and you're able to articulate yourself very well. And that sort of communication skill is something that's very valuable. Any other physics that anyone would like to talk about?